Okay, everybody, this is my last video that I'm going to do here concerning inverse matrices, but specifically the inverse of a 2 by 2 matrix. So we're going to talk about the inverse of a 2 by 2 square matrix. Um, the neat thing about taking the inverse of a 2 by 2 matrix is that it's very basic in the sense that we have actually a formula we can use. But we say this, we say given some square matrix A, and we'll, of course, talking about a 2 by 2, we'll say A is a square matrix such that we have elements A, B, C, and D within the matrix. Okay, we're going to start first by defining what we're going to refer to as the determinant. Determinant. Kind of sounds like it's going to tell you everything you'd ever want to know about this. But the determinant of the matrix. Now, what I'm going to tell you is this. I'm not going to go in depth into what the determinant is or its uses. More of just how to find it with a 2 by 2 for now until I post further videos on the determinant of matrices, or determinants rather, sorry, plural. But anyways, the determinant of this matrix A, and we're going to define the determinant of A. We kind of write this as a big fat bar around it. It's almost like magnitude when you talk about vectors. But the determinant of A is bar A, or absolute value bars is what it looks like. But we refer to it as AD minus BC. Okay, AD minus BC. So here's the thing about it. We talk about its determinant being AD minus BC. I have a few clauses to build in here, but we say if, okay? So we say if AD minus BC, which is the determinant of A, okay, for a 2 by 2 is equal to 0, then we refer to this as a singular matrix, okay? We're going to find out here in a minute that that's not necessarily the best thing in the world. It's not a horrible thing, but in terms of finding inverses, it means that one does not exist. But if AD minus BC, which is the determinant of A, does not equal 0, then we say this is a non-singular matrix, which is totally awesome because we want to find inverses. So let's keep this idea of determinant in mind for now. But we say, okay, so given this matrix A, what we're going to do is we're going to define the inverse of A inverse, as being this. Okay, now keep a close eye on this because there are some patterns going on you really want to pay attention to, but it's really kind of straightforward. So we say, given A inverse, pardon me, let's just do this. We say, how about this? How about, you know what, that was fine. I don't know what I was thinking. A inverse, we're going to define it this way. We say it is 1 over the determinant of A. See, that's what I was thinking of. And this is times matrix, sorry, times, I'm going to push real hard on my pen, times the matrix dA. So the first thing I want you to notice is this. All we did was kind of invert the main diagonal here. So the very first entry on the main diagonal and the last entry of the main diagonal, we flip them around, and what we're going to do is we're going to leave these other two entries here stationary, but what we're going to do is we're going to negate them. Okay, and what we're going to do is we're going to define this as being the inverse matrix of A. Now, of course, as you've seen in the last videos, this is not the only way to find A inverse, but it is a very convenient way, given the fact that there's a lot less manipulation going on. We just have to invert the main diagonal and negate the opposing diagonal, and then multiply that by the scalar 1 over the determinant of the original matrix. Okay, so all this being said, here's what we'll do. We'll just go ahead and pop open a new window here. Just in case you didn't know, things typically go faster with sound effects. It's kind of like painting your car red. It just goes faster, doesn't it? Okay, anyways, I feel like Bob Ross here. We're going to go ahead and magnify this for us for the sake of this. But given that last definition, recall that we said given a matrix A, we're going to refer to its inverse, A inverse, as being 1 over the determinant of A times the matrix dA, where we flipped the main diagonal and negated the opposing diagonal. Okay, so what we'll do is, how about we generate a couple of matrices here? We'll call this matrix A. So matrix A is a 2 by 2, of course. This only applies to 2 by 2s, this idea of finding an inverse in this manner. So 3, negative 1, we'll make this like negative 2 and 2. And then we'll call this matrix B down here 2 by 2. I don't know if anybody sees where I'm going with this one here, but I created two matrices for a reason, or I am creating them. 3, negative 1, and of course negative 6, 2. Of course you would say that, but anyways, okay, so let's start with this. Over here, we're going to go ahead and find the determinant of A, which we said we defined as being the main diagonal, basically the product of the main diagonal here. So we say 2 times 3 is 6 minus BC. So we say negative 2 times negative 1 is, of course, positive 2, but we're subtracting out positive 2, so we say its determinant is 4. And down here we say, okay, so the determinant of B is the product of the main diagonal. So we say 3 times 2 is 6, of course, minus. Now, check this out. We've got negative 6 times negative 1. That's a negative 1 there. It's positive 6. 6 minus 6 is... That's right, 0. So recall from what I just mentioned in the previous window that we're going to call this a singular matrix. And if you remember from my last video, we say singular matrices, I'm sorry to tell you this, but they just don't have inverses. But this is where we're going to kind of discuss why. But anyways, now that we have their determinants, we're going to kind of run with this here. But we say matrix A. Okay, so in order to find its inverse, we say A inverse. We're going to call this 1 over its determinant, which was 4, times the original matrix where we have inverted the main diagonal. So now it's 2, 3 down the main diagonal, and we're going to negate the opposing, where now this would be a positive 2 and a positive 1. Okay, now I can go ahead and multiply this 1, 4 through, or you can leave it out there for now. It's kind of like having a factored expression, you know. You might as well leave it at factored sometimes. It's just kind of cleaner. But if you multiply this through, I do want you to see that this would become 2/4 or 1/2. 1/2, okay, so we say 1 times 1/4 is a fourth. Then we say 1/4 times 2 again is a half. And then we say down here 4 times 3, now we have 3/4. Okay, and then the nice thing about this is, given this inverse matrix now, you can take this times the original A matrix, and you'll find that you get dun, 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 the identity matrix, which is what we are after, I don't know, it just seems like all the time. So now moving on, let's talk about B inverse. Now B inverse, God, I hate to spoil it so upfront like, but we say this would be 1 over its determinant, which was 0, so you already see what's going to happen there. But go ahead and invert the main diagonal, which would become 2, 3, since the original was 3, 2, and we'll negate the opposing, so this is now positive 6, this is a positive 1. But the fact of the matter is this: we have attempted to do something we're not supposed to do, which is divide by 0. So we say if that's the case, it's undefined. Undefined. So we say literally, yes, B inverse is undefined, and we can also say this: D and E, fun letters to write out in math, but does not exist. Okay. So we say if a matrix is singular, its matrix does not exist because of the fact that, you know, we would have been dividing by 0. But given a 2 by 2, if it is non-singular, like this one up here had a non-zero determinant, the nice thing about it is this: its identity matrix. Its inverse matrix exists, and it is easily found just by flipping the main diagonal, negating the opposing, and then multiplying by 1 over its determinant. So this is kind of a nifty way to do things, and I hope you enjoy it. Enjoy the video.